Got it. Let's see. Okay, I think we are live.
Okay.
Yes.
Hello, world.
Okay, nice. So, since we are live, hi everyone. I think we are live. Okay, let me turn off the audio of the live. Okay. Since we are live, so hi everyone. Thank you for joining this new event from Open Neuromorphing. Today we have with us Timoleon Moraitis. Timoleon will tell us about the research is being carried on both in industry and in academia, and about neuromorphic computing with a little part of SNNs and online learning. So, as you might already know him, Timoleon got his PhD in Zurich from the Institute of Neuroinformatics. And from there, he went to lead technical teams in both IBM and Huawei, always talking about efficient ways of implementing machine learning models on an efficient platforms. But I will now leave the word to Timoleon. And that's basically it from my side. So, Timon, please go on.
All right. Thanks. Thank you for the introduction, and of course also for the invitation. It's a pleasure to be here and presenting our work. Just a small correction, but at IBM I wasn't really leading a team, even though I was also supervising some students and so on. But yeah, at Huawei it was my first kind of group leader position.
Sorry.
All right, but yeah, so yeah, the talk is has this sort of intriguing title, Making Neuromorphic Computing Mainstream. And let's see, first of all, just in case there's anyone in the audience who doesn't know what neuromorphic computing is, it's a quite exciting field because it's composed of many fields. In fact, it's about taking inspiration from the brain and how it works, and then using that knowledge in order to make sensors, processors, like computing processors, and then it also involves dealing with special materials so device physics that you can then use to actually perform computation in using the atoms of actual nanodevices. So all that sounds, I mean, and is quite exciting. So the state of the art in the field involves multiple processors from academia as well as from the industry. And I mean, I just put here some pictures that, you know, they cannot be representative because the field has been actually exploding. So I want to to stress that it's actually the advances have been impressive in all these aspects. Particular focus has been given on the aspect of efficiency. So this type of biological inspiration promises to actually decrease energy consumption of AI. A particular type of aspect of biological property that is focused on often is this spiking aspect. So spiking neural networks, which is a specific way of how neurons in the brain communicate, which is pulses that can be very efficient. Right. So, however, people somewhat outside our field, for example, Jan LeCun, who is one of the recipients of the Turing Award for his contributions to deep learning, relatively recently, even though now it's a long time actually, said exactly why build chips for algorithms that don't work. It is, you know, it is kind of harsh, but maybe there's some merit to it to some extent, right? So just to explain this, let's take a case study. Let's take this one of some very recent, very impressive pieces of work. Actually, it was led by Jason, who's in the audience, and you know, performed by others as well, about Spike GPT. This is a spiking version of a transformer or sort of analog, something analogous to a transformer, which is the underlying, let's say, model of ChatGPT and so on. So making it spiking promised, and actually in the results that they show that it has the potential to increase efficiency by 20 times, which is actually quite impressive. It's right. However, if we are fair to our users or prospective customers and so on, there is an asterisk there. There's like fine print. So what it would be, that fine print, is that type of efficiency would be possible on hardware that is not the common hardware that is used today. It's on hardware that is not yet available. Then that paper actually shows very strong performance, but still it has performance trade-offs that, so if you want to compete with what is currently out there, this might be important. And in fact, since the paper was out, and because it's in such a hot field, if you search on Google Scholar for other approaches for efficiency of transformers, there's hundreds, if not thousands, of papers, which actually, if you combine them, you get perhaps better efficiency advantages. Some techniques include minimizing the memory accesses on the GPU by optimizing the CUDA kernels, sparsity, quantization, speculative decoding, and other kinds of methods. And these are specifically for the type of transformer architecture. But I don't mean to single out this paper. Actually, I singled it out exactly because it's an amazing piece of work. It's not because it lacks anything, but it's actually it's a common, that could be a criticism that would be common to many neuromorphic algorithms. So what, in fact, I would claim that this might, it may be difficult to actually displace the currently mainstream technology with this type of approach, because, right, I think that was clear. And I think what we would need to actually become mainstream, we will need advantages today. So not theoretical in some hardware platform that is not yet used. We would need not performance trade-offs, but we would need to actually show improvements in performance. And in fact, if the advantages we should show shouldn't be possible also with other technologies, which are actually common nowadays, but they should be somewhat unique to neuromorphic computing. So is such a thing even possible? Well, yes, it is. I would like to say. So let's see how. In order to specify how that could be possible, let's examine the underlying reason for this kind of, let's say, criticism or issues of our common approaches. So usually these neuromorphic approaches, actually, what they do is they take existing AI methods and they try to approximate them, for example, by making them spiking instead of having continuously valued activations in order to improve efficiency. But this leads to an unavoidable trade-off. By merely approximating existing methods, the performance is bounded. Oh, there was some pop-up here with me. Let me go back to my window. All right. In addition, that goal is actually unnecessarily narrow. Biology is not it doesn't only have the advantage of energy efficiency, it offers so many other things that are not yet present in mainstream AI. So an alternative would be to actually, instead of approximating existing methods, to devise new methods that are based on biological mechanisms. And then that could lead to actually improved performance, and not only in terms of efficiency, but actually also in terms of accuracy, generalization, speed, and so on, and which are actually true for the human brain, and presumably if we were to imitate these mechanisms, we would also bring in those improvements to AI, and then the possibility of an efficient implementation in hardware is a sort of a given, because by virtue of these mechanisms being implemented in biology, we need to emulate them. Right now, in a nutshell, I would say the common neuromorphic paradigm is to actually treat performance and efficiency as a trade-off. So it's performance versus efficiency. And the proposal here is to achieve performance through efficiency, to increase even performance through mechanisms that are efficient by being biological. So just to give since it's a sort of, we're supposed to be in a sort of workshop here, let's try to make it a sort of tutorial, even though it will make more sense once we actually show examples of it. But what would be the recipe to do that? It would be, we would have to choose some mechanisms from biology that are still unexploited in AI, right? That's point one. Then we would need to have a sort of intuition or a hypothesis about what is the advantage that this neurosynaptic mechanism could bring. Third, we will need to actually mathematically model that, since that is not yet common or understood. We would have to understand it mathematically. Then fourth, we would need to actually demonstrate that this advantage that we sort of hypothesized is actually present, or at least in toy problems. So the first outcome of that would be that we actually would contribute to neuroscience, which we maybe have not been doing with some of the approaches, right, anymore. Then a further point would be to actually take these mechanisms that are not yet present in conventional AI and combine them with deep learning or conventional methods in order to actually also get the high performance that is necessary, and then apply them in practical real-world problems. So the result of that would be to actually improve the state of the art in AI. And then these advantages will then be present even on GPUs, which is we wouldn't need to change the whole hardware yet. And then the applicability would be actually possible today, and then possibly in actual products. And then as a next step, having proven the advantages of even beyond efficiency, then there is no reason not to also do the efficient implementation in specialized hardware. And in fact, it wouldn't just be, in this case, efficient because the hardware is specialized, but that efficiency would not be possible with other kind of efficiency optimization methods, because in this case, the hardware, the neuromorphic mechanism is not merely an addition to make things efficient. It is the reason for high performance. So its hardware version would be the optimal version. So it would be unbeatable also in terms of efficiency. Now, of course, it should be made clear that this is a difficult task, right? There are all these disciplines involved here. There's like theoretical machine learning, applied deep learning, neuroscience. There's material physics if you actually go and try to implement these in hardware. There's chip design and all that. So it's truly a difficult task. But I would say that it also has the advantage of that it does have the advantage of actually making taking the direction of maximal impact, I would say, let's see some examples. So the examples I'll show, we could categorize them in 4 pillars. One would be a kind of learning theory, dynamic problems, then making intelligence embodied, and then how to make these AI models faster. Right. So let's jump into the first one. Backpropagation is the core algorithm in deep learning or in conventional deep learning. And however, it is notoriously non-local, and it also has other inefficiencies that actually prevent truly neuromorphic learning. So non-local means that you need to have information in order to update the connection between the neurons. You need to have information about big parts of the network that are not local to that synapse or that connection. And I mean, the actual issues, they can be more specific, more narrowed down into the issue of weight transport, of non-locality, as we said, or the fact that the updates are time locked, and also various definitions of supervision or that is necessary in order to train these networks with backpropagation. Right. So because of these limitations, there have been multiple high-profile approximations to backpropagation. You know, many of them from companies like DeepMind, from very important academic groups, and so on. However, they actually all have achieved quite low performance. And in this table, it's results on CIFAR-10, which is an image recognition, a relatively simple image recognition data set. And they're also only partly efficient. So almost none of them actually deal with all the issues of backpropagation. Now, this issue was also pointed out by Jeff Hinton at Neurips last year in his keynote speech, where he actually also presented another alternative algorithm, which also has some of these issues. Right. So now our contribution in this direction is that we presented in that paper in the journal Neuromorphic Computing and Engineering last year, which we call SoftHeb. The reason we call it like that is because it's based on Hebbian plasticity. Hebbian means essentially all the information. It's local, just to simplify it quite a lot. But anyway, it's about having local plasticity to the synapse, as well as a structure that can be described as a soft winner-take-all. So both of these are actually entirely biologically plausible. There is a strong evidence for the presence of both. So this kind of circuit design of the network, the winner-take-all aspect, is actually present in the cortex based on many types of evidence, anatomical and electrophysiological, as well as Hebbian plasticity is sort of one of the simplest rules. So essentially, the assumptions that are necessary are in order for this thing to be actually possible in biology are really minimal. So in some sense, it's actually as biologically plausible as a learning rule could get. In that paper, which was mostly theoretical, we showed that you can actually use that to minimize cross entropy, which is a common loss function for deep learning, without using backpropagation. In this case, and from a practical perspective, we showed that it had some learning speed advantages, as well as some striking robustness to adversarial attacks, which is another notorious issue of backpropagation-based networks. Right, but this was mostly theoretical. It was actually limited on a single layer, that paper. So moving on, we actually by combining it with some additional mechanisms, we then applied it to multi-layer networks. So it actually, we did previously, this kind of the general concept of Hebbian plasticity and winner-take-all network is not new. The specific formulation of it is new. And previously, it was not possible to use it to train deep networks. In this case, we managed to do that. It is also an unsupervised learning rule. And it actually, in this table, again, it's only CIFAR-10, but in this case, we outperformed all the previous approaches, as well as in other data sets, including ImageNet, which is considered one of the, it's a quite big data set anyway, where previous such algorithms were not applicable. And arguably, this would be also the most efficient implementation in hardware, because it needs nothing to be backpropagated, no signal to no global communication of any kind of signal from final layers towards the first ones. Right, that was published at ICLR as a spotlight paper, which is one of the sort of mainstream AI conferences. Well, you can actually show that this doesn't need, it does achieve some efficiency already in GPUs as well by reducing the operations and memory usage and so on. But of course, the most efficient version would be in hardware. But now let's focus a bit on what I said about the advantage of dealing with adversarial attacks. So this is from CLIP. CLIP is a model from OpenAI. It's now it could be considered old, but it's also quite impressive. You show it an image, this image here, and then it can tell you it's a cat wearing a suit and tie with green eyes. No, it's really detailed description, which is actually correct. But then you show it, if you show it the digit 4, then it will correctly tell you it's the digit 4. But if you just add Gaussian noise, nothing, not any very strong adversarial attack, just noise, then it says it's a picture of a person doing a yoga pose, which is, it's funny, but it is a well-known limitation of these networks, and you wouldn't expect it to be the case for such a model. But then this very simple network, even a single layer with another classifier on top, that is trained with our software learning rule, it dealt fine with this kind of noise. As well, in the paper, we have actually analysis, including strong adversarial attacks, which assume knowledge of the whole network and its details. So, and this is just, I just did it also with GPT-4, since the other one is an older model, and it also says, it says it's some heat map or some form of data visualization and so on. So it also failed, at least in this. I tried again at a different time, and then it said it did it correctly, but still, and there are other caveats that could be made about it, but still, I think it's you get the point. Right, so we already spoke about a few advantages of this kind of algorithm, but is it actually possible to implement it in hardware? Well, in the past we did it before, so not SoftHeb itself, but other Hebbian winner-take-all rules, we did implement them in memristive devices. These devices are nanodevices that can actually they store a memory as a resistance, and that resistance value can be changed depending on the pulse that you apply. And then you can use these as synapses, connections between neurons, and then you can use the property that you can change them in order to implement learning rules. So by using a sort of Hebbian learning rule and a winner-take-all connectivity, in the past we did show that it's possible to use them for a similar type of learning rule. So presumably it will be possible also to do SoftHeb itself. However, would it make sense to just jump now and go and build chips with in-memory learning? This is maybe still questionable, because there are some unresolved challenges that are quite important. So we only showed it on a very constrained architecture. In order to make it work in deep networks, we had to do a very kind of weird network using a specific structure that is not, we wouldn't know, for example, now how to train a transformer using SoftHeb, or other networks for that matter. And also, we only showed it on some image recognition datasets. And in addition, even though it surpassed the state of the art among all these kind of efficient implementation or approximations of backpropagation and more biologically plausible rules, it is still very low, it achieves very low performance compared to the state of the art in actual backpropagation. And the networks, even though they were as deep as other approaches that have similar goals, they are shallow, like 5 hidden layers or so. So yeah, it may not make sense, but so let's see. I see Fabrizio is raising his hand.
Yes, I am here to report a question from YouTube. So the question is, what is the reason for these wrong outputs when conducting adversarial attacks?
Well,
the pixelated means the image means.
Right, I understand. So this is so it would be even the specific example I showed may not even qualify as an adversarial attack. It's just noise, right? But adversarial attacks are actually so it's a field on its own, understanding how to deal with them, how to make networks be less susceptible to those, and so on. So it's far from being fully understood, but my sort of simple explanation will be that training with backpropagation sort of how to say, it specializes on a very specific configuration of inputs that then if you slightly change it in something that also was not in the data set itself, then it can be very confusing for the network. It would be, I wouldn't be able to give a good answer right now by waving my hands. We will have to, there are various theories and various ways of dealing with these things as well. So yeah, I don't think this is a very satisfactory answer, but I think the person who asked it can start looking it up and spend a few days on it.
Yes, thanks. There is just another question. Have you tried on few short learning or semi-supervised learning task? I think it refers to SoftTab.
Few short learning was or semi-supervised learning. Well, so something I did not mention is that, which is related, is that we actually were able to outperform these other approaches in a single epoch of training. So the data set was presented only once, the training data set, and it's already reached that. So it is another advantage of efficiency in some way, which is a different type of efficiency than commonly understood. So in that sense, it is a sort of few-shot learning. But exactly what is meant commonly by few-shot learning, we have not tried. And also this semi-supervised, we haven't tried either. It was fully unsupervised, so no labels at all. We actually tried fine-tuning with some labels, and further by using then backpropagation to fine-tune the network that was trained with SOTA, and it further improved the performance. I'm sure there are all kinds of things that you could do in order to maybe improve it by adding some supervision as well. Right. So is there any other questions so far?
The last one is if you have tried it with SNNs and if you foresee any difficulties using it on there.
Right. So, well, in this case, I think part of our kind of strategy has been to focus on the items that are, of interest. So here, if we did it first in SNNs, it wouldn't add something to it, maybe other than saying it can also be spiking. Since the mechanism is useful without spikes, it makes it clear what the mechanism itself is that makes this thing work, which is not spikes. But it could be done in a spiking network. It would probably need, there can be the most, I guess the most naive implementation would be to rate code everything and then try to do the exact same thing, just using a few spikes in order to encode some value X. But we haven't tried it, to answer that question.
Okay. No more questions. Right.
All right. Yeah. So where were we? All right. So moving on to some more kind of dynamic types of problems than the static image recognition. So one thing that we, again, remember the kind of recipe that I presented was we need to think about properties that are present in biology, and they have some analogy to some problem for which they would presumably be useful to solve it. So we observed that the environment, very commonly in dynamic settings, it has some properties that match the dynamics of that are within synapses. So in fact, just to make to be as brief as possible about it, when you observe a cat, then its most likely future observation would not be like that, but it would actually, or like that, it would be something that is centered on what you just saw. So there's a sort of associative relationship between a present form of an object and a future form of it. And then secondly, the probability of observing the same object in the future, it decreases because objects move in your environment. So in synapses, you have this associative learning rules that are Hebbian, as we already mentioned, in spiking versions. Kind of associative for STDP, for example. But then very commonly, before the strengthening of a synapse is actually consolidated, that weight update actually decays. So this is a short-term aspect of synaptic plasticity. So this could be called a type of short-term associative plasticity or short-term STDP in this case. And in fact, by describing these things mathematically, we showed that this short-term type of plasticity is the mathematically optimal solution to modeling such an environment, predicting it and then inferring also what you see in a frame. So it turned out that algorithm can be described as an elastic clustering algorithm, where you have clusters defined by centroids, and then these centroids are allowed to move elastically around their position. But then we went further and showed that this is equivalent to performing cortical computations with short-term STDP, where you actually learn these fixed positions with standard STDP, and they're fixed. But then you allow these to move as observations come. These are the centroid is allowed to move towards the observation, and then elastically return in the short term back to its original fixed position. And then in order to make this a sort of clustering algorithm, you need a kind of competition between the different clusters, which is realized by these cortical winner-take-all networks that I was also mentioning before. So the idea here is you take this winner-take-all network, you train it with long-term STDP in an offline phase, and then when you do inference, you have your some video, for example, you observe the environment with all these things moving around you. You still allow the synapses to update themselves and in this short-term way, while having inhibition across the neurons to implement this winner-take-all connectivity. These are the details of the plasticity rule, and it's the spike timing dependence that we also have there in the spiking version of it, which is a short-term spike timing dependent plasticity. All right, and then so that was about mathematics and kind of theoretical machine learning or theoretical neuroscience. But then we actually kind of devised a data set that would be suitable for this thing, which is MNIST, but in a sort of video where you have occlusions coming in front of the digits randomly, and then you have noise, and then you have a different digit, and all this thing is presented continuously. So the idea is you train your network with STDP on MNIST itself, just to classify MNIST digits, and then you wanted to be able to classify these things. So, for example, if you show the standard network this image, it would be impossible to recognize it, right? Because it's just, how can you know if it's a zero if you don't have some sort of memory for the past? And again, we follow this kind of approach, and so in this case, what happens if you plot the synaptic efficacies, these are strengthened, and then they, for example, if you take this synapse up here, when the digit, this is something that has a neuron that has learned to recognize digit 0, and then you show it digit 0, and these weights are strengthened. But then if this occlusion comes here, then this parts up here start weakening. But in any case, this strengthening, which is short term, so that the neuron can return to its original idea of what digit 0 is, allowed that cortical microcircuit to actually recognize this very distorted and previously unseen patterns. These were not present in the training dataset by exploiting the temporal continuity of the inference dataset. All right, so, and then we actually used networks of similar size that are more conventional, including CNNs and LSTMs, and that spiking network in this case was able to outperform them, even when these were trained on that temporal dataset. Even though this was not trained on the temporal dataset, but it was allowed to adapt to it. All right, so this. I should maybe accelerate a bit since there's a few things I'd like to show, but Anyway, yeah, it outperforms its ANNs, and it's actually purely neuromorphic and biologically modeled. But it's still a very small problem, and it was actually tailored to be suitable for this network and difficult for the ANNs. And there are other improvements that you could add to the ANNs themselves. But still, I think it's making it is remarkable that such a simple network can actually challenge ANNs at all. Right. So moving on, in order to make it a bit more practical and not just you know, a toy demonstration, we went on and actually applied what is called meta-learning. So it is about learning to learn. So if this short-term plasticity is about learning, then training, this plasticity rule has some parameters. For example, the time constant of the decay, or the strength of the jump for each Hebbian update. So if you train the plasticity's parameters, then it's a type of meta-learning. In this case, it will be learning to learn and forget. So we're learning to learn, but also learning to how to forget, because we're training the decay of the weight updates. In order to achieve that, we formulated this plasticity, this neuron with plasticity, with short-term plasticity synapses as a type of recurrent model, where there's recurrency within each synapse to represent the state, or the short-term state of the weights. And we call that the short-term plasticity neuron. And using that, we were able to apply these this kind of neuromorphic mechanism to advanced machine learning problems. So, all right. Sorry, my computer is glitching. All right. So what I mean by, so there we use a sort of toy language processing task here, which was previously used by an attention-based mechanism by Hinton and Jimmy Ba and others. Back then, we had this kind of maze where the maze itself is changing and the reward is changing its position. So you need to not only learn how to find it, but then you need to learn again its new position, which has this nested kind of meta aspect where meta learning is useful. We used it for kind of Atari games, as well as this kind of simulated robotics. And we compared to several other models that were previously, you know, even designed for these tasks. They also include some kind of adaptability, but we also include had like more conventional, like LSTM and so on. Our kind of this STPN, short-term plasticity neuron, outperformed all models in all tasks. And these are actually tasks that are usually out of reach for neuromorphic computing, right? But in this case, by following that kind of recipe where we actually combine it with deep learning, right, we were able to actually show it as practical and actually improving the state of the art in conventional AI. And this was, by the way, at ICML, which is another of these kind of mainstream AI conferences, right? And then just to explain that even these problems that are challenging are actually maybe not practical, but similar algorithms, like we actually did reinforcement learning and so on, can be used to train robots to learn. For example, in this case, it was the algorithm that we used for our reinforcement learning was used in this case with a recurrent network that we outperformed. In that case, to train to let a robot learn to walk in a few minutes. Just to say that this is also practically applicable in truly real-world problems. But another so quite interesting aspect of it, which is even more neuromorphic, is that this short-term depression of the synaptic weights, or rather short-term facilitation that is then depressed, it actually introduces a new method for energy efficiency of synaptic weights. The reason is that as the neuron is now able to turn on and off individual synapses at different time points, then in a neuromorphic implementation, it means that it shuts on and off individual currents, and that shutting off of individual synapses is what enables it to perform very well but it would presumably also then reduce the energy consumption of the forward propagation just by using, standard physics equations. You can calculate that. And we went on and calculated that, and indeed that intuition turned out correct. So the STPN would be the most efficient model of all the others, with respect to that type of energy consumption. So this is a demonstration of how we achieve performance through efficiency, and it's not really one or the other. In the past, we actually had some demonstrations of short-term plasticity with memristors. In that case, it was the long-term weight was in memristors, whereas the short-term aspect of it was in software, and we applied it in some weather classification problem. And currently, we're also working with colleagues from ETH, Alexander Semboris and Christoph Weilenmann. We're preparing a manuscript where we're actually showing also that kind of meta-learning aspect where you can tune the parameters of the short-term plasticity in devices that are responsive to both electricity and light. Right. And last year, we also published this paper with Ghazi Sarwat and others from IBM, where we emulated short-term plasticity, where the atomic configuration of these nanodevices was storing the long-term weight, whereas by applying an electrical field and exploiting the field effects, we were able to have these short-term effects as well present, which modulate the conductance of the device, and therefore you can use it as a synapse with short-term plasticity. Right, then the kind of that reinforcement learning aspect that we used in these models, we have also shown that it's possible to implement it in memristive nanodevices, which these devices actually also respond to both electricity and light. And in that case, we applied, for example, a reward using light and then electricity in order to apply the weight update. So we implemented a three-factor learning rule, which is then can be used to realize reinforcement learning in devices like these. And we actually showed that we can train a model to learn to navigate this simple maze. In that case, it wasn't that more complicated maze, but it was a simpler one as a proof of concept. All right, moving on, remaining in the sort of embodied intelligence aspect of things, the idea here is coming from sensory motor neuroscience. So something that is interesting is, do you know why you cannot tickle yourself? If you try to tickle yourself, you cannot do it. And the reason is because your brain, it sends a command to your muscles in order to tickle yourself, but it also sends a copy of that command to itself, and then using that, it can predict the outcome of it and then cancel it. So it cancels the tickling sensation by sending a copy of this efferent output. So that's called an efference copy, whereas there's a motor command sent to the environment. And then the idea here, well, by the way, this is not our theory. It's well established that that kind of signal exists in humans and frogs and other animals and so on. But its proven roles were different ones than the one that we hypothesized here, and we showed it's possible at least in models. So the idea here was to use this signal as a self-supervising signal. So as a sort of self-provided label. So if your network is not merely provided with inputs that it's supposed to learn from, but it's actually acting on the environment and it's able to transform it and then decide when to look at a different object, or then decide how to look at it from a different angle, and then it has access to these transformations, and it can use these transformations as labels, self-supervisory labels, to improve the learning. So that was the idea, and we actually, we showed that we implemented using ResNets and by the way, the theoretical aspect of the model of the paper showed that this is actually a generalization of well-established self-supervised learning algorithms, and it also unifies them in a framework that it says that they can be in biology. All these could be implemented by inference copies. And then it also extends them. And this extension, we showed that it actually improves their performance, including in ImageNet and other data sets, as well as some audio cases and so on. And that was consistent in all cases that we tried. And in fact, some details that I didn't mention here that are biologically inspired, were also important for achieving good performance, so which is also interesting. And the last kind of pillar that I said I would mention is this achieving fast inference, where we actually get into. So far I spoke very little about spiking networks, but here in this case we actually use spikes in a somewhat unconventional way. Right. So just as a reminder, the biological spiking networks, they can encode information in the timing of these pulses that are spikes, and they're fast and efficient, but they're commonly less accurate than the conventional ones. On the other hand, artificial neural networks, even the recurrent ones that deal with time, they usually focus on the network output's magnitude, not the timing of it. So they are not trained to determine when to produce an output, but they are more accurate than SNNs. And our goal here was to actually get the best of both worlds. We wanted to improve the accuracy and the applicability of spike-based networks, but we also wanted to improve the state of the art in standard conventional neural networks, like recurrent ones, by adding these spike-based methods. So the idea is that imagine you have an audio signal that is a time series, and you provide it to a recurrent network. And then you have some hidden states in the recurrent network, and then you have some output layer. Well, you just apply a threshold at these output neurons, which then makes those output neurons spiking. So that first spike is when you apply your label that you backpropagate through time. So instead of just providing the whole training example and then backpropagating through time, you do this kind of spike-triggered backprop at the first spike, which could be said that is the spike of rank 1, which based on that we call this method rank coding, because that rank is also encoding the label. So the first spike is also, after you've trained it, it's what encodes the inferred label. So we use just standard cross entropy as a loss function to train the network, and use standard backpropagation for time. The only thing we did is we did the output layer spiking and triggering the output. And then using that, during training, you can see that the accuracy is increasing because of, we train it to minimize cross entropy, but also the first spike time is decreasing. Kind of for free. We didn't actually tell the network try and minimize the first spike's timing, but it turns out it does so. And in the paper we also have some theoretical derivation that explains why that happens. But the result is that the resulting network has accurate but also fast responses. So we tested in some problems that we designed in order to understand it, but then we also tested it in actual commonly used benchmarks, like this temporal MNIST, where the intensity of the digit is encoded as in the time of a spike that's provided. And this method outperformed all previous spiking networks in this benchmark. And then we also applied it on keyword spotting on Google speech commands. We showed that there are methods to actually make it even faster. While if you wanted to allow to also, if you allow it to decrease a bit the accuracy, you can make it even faster. So you can tune the speed accuracy trade-off. But the main result is that you can actually, you don't have to trade off accuracy, but you can actually improve the speed of these recurrent networks as well. So it improves spiking networks in a sense, even though it's not a fully spiking network, but compared to other previous works with spikes, it has higher accuracy, but compared to networks without spikes, it has faster responses. So it kind of gets the best of both worlds, including in a sort of real-world application like keyword spotting. Right, I think this summary I already gave it. So in a conclusion, I would say that the neuromorphic computing perhaps should be. Again, my computer is doing some weird things today. Let me bring back up. All right, here it is. Okay, so spikes is one very useful mechanism, but there are more. There's local plasticity, there's shortterm plasticity, there's difference copies, and each of them has different ways of using it and different versions of it. And if you apply it in a careful way, you can show things that were not previously possible that are beyond efficiency, right? So it's not only about energy efficiency, it's also about data efficiency, it's about speed, it's about learning without supervision, about adaptability, about increased generalization and robustness. And all these are advantages not within the neuromorphic niche, but advantages compared to the broader state of the art in AI, right? So, and in real world applications as well. So, again, to repeat that, biological efficiency does not have to be necessarily viewed as a constraint on performance, but it can actually bring advantages in performance. And since it is both efficient and well-performing, it could become the mainstream of AI. So there is some evidence for that if you want to be optimistic. Well, one is that, these conferences where these were published are, we kind of targeted these communities that are, and we targeted their own benchmarks which we outperformed in these mainstream AI communities, and then things that are I couldn't talk about publicly now, but some of these things that we actually did work with the product lines in order to put them in actual products, because they have these advantages that are useful today, right? So that's the recipe again that we said, and again it is a very kind of challenging thing, but I think it's worth actually taking this kind of systematic approach in order to get the maximum benefit from neuromorphic computing. Yeah, with that, I'd like to acknowledge that this is not only my own work, but there were many people involved and many institutions as well. And with that, I'd like to thank you again for having me here and for listening to all that.
Thank you, Dimos. So let's check if we have any questions. Yeah, there was one on a previous slide. It's always about SoftTab. So he's saying the brain uses both unsupervised and feedback. So it will be interesting to add some partial feedback to the SoftTab network to improve accuracy. Do you think that is the case?
I do think there are ways to improve accuracy by using some supervision, as I said, as was asked also before, or some other kinds of feedback. In this case, yeah, I think just to be brief, yeah, I think so. But it's also interesting that without any feedback, we outperformed previous methods that rely on feedback. So there might also be scenarios where the feedback is somewhat competing with what is learned bottom up. This I wouldn't be surprised if this happened. we have seen this, for example, in other cases of like other local learning algorithms and that are becoming popular today. That if you try to combine supervision with some local self-supervisory signal, that you get worse results than both. So, but I think that some version of that would improve results here.
Okay, thanks. There is another question. Would we be capable of dropping the overall power voltage on these units' computers? I think it refers to neuromorphic hardware. Granted, if you can emulate the human neurological system, they say it takes less than 9 volts to run a human brain.
Can you repeat the first part of the question, the main part?
The first part, to summarize, I think would we be capable of dropping the voltage on these new neuromorphic computers, let's say, if we can emulate the human neurological system?
Right. So this is the whole idea. Is about actually dealing with pure currents, reducing the voltages that are necessary to do this learning and all this inference and so on. I mean, I didn't mention any voltages in order to say we could reduce them. Yeah, I mean,
I think the question was, I think the question was more of the brain works with 20 watts.
Yeah.
Can we foresee an actual computer being as powerful as the brain with that power budget? I think that was the question, maybe.
Right. Yeah. I mean, I potentially in some far future we could foresee that, or maybe in a nearer future that can be achieved with even lower power, but actually wouldn't be doing all what the brain does, right? So our brain is doing, like, it's controlling a robot right now. It's speaking, it's recognizing images, voice, and all that in this 2 liters with this maybe 10 or 20 watts. So that is a very far future, but that, yeah, indeed, that is part of the motivation, is understanding how the brain does that and also being able to do that. And yeah, these algorithms and then their hardware realization is about getting there, but we are far from there.
Okay.
Let me come in with a question as well. Yeah, I found that wonderfully refreshing. That was really nice. I really like some of your kind of mantras in there, where take the biological principle that makes the most sense. Don't constrain yourself to spiking, which, if I can be frank for a minute, is probably something that the neuromorphic community has somewhat overfit to. We're definitely focusing maybe too much on spiking and not so much on a lot of the cool principles that you've sort of brought up here. And I also like the idea that we've got, well, NVIDIA had this beautiful monopoly on GPUs, so we may as well take advantage of that and see if we can build neuromorphic algorithms that can actually make sense on hardware that is presently accessible. So that's awesome. I really liked what you presented here. My very high level question is related to the fact that, so there are theories that backpropagation maximizes information transfer. We know that it's kind of like the chainsaw of deep learning, optimizes whatever the hell you want. Is there some sort of, so my current intuition on why biologically plausible learning mechanisms, why they could potentially outperform backprop from beyond an efficiency standpoint, more from like a loss convergence or some sort of convergence metric. My intuition on why they could work well or better than backprop is, given a set of resources, given a finite amount of time, then that's where these types of algorithms could shine. Given infinite resources, then yeah, use the chainsaw. Is there any other intuition that you've kind of gained over the years of building local, semi-local, mixed learning rules as to why or how these could outperform backprop?
Yeah, so there are several potential ideas. Some of them would be speculative. Some of them, not just about their explanation, but also whether they're even possible. But some of them we have demonstrated. For example, we demonstrated the the robustness in some cases. We've demonstrated a very high speed of learning within a single epoch. And these are like, you could go into the math of what it is that this learning rule optimizes and how it does that. And then it could provide some partial or potential explanation. But in general, I think it is a sort of, as you said, it is, as you said, you said that these kind of conventional learning algorithms for like backprop and so on, they work very well, have infinite resources and time. But this is not the only thing that differs between this assumption and what our brain is supposed to do. There are other things that differ, and they are that it operates on noisy kind of hardware or wetware. It operates on ever-changing wetware and hardware. It operates on dynamic environments, right? So it needs to keep constantly adapting. And these things need to happen from the bottom up. You cannot, observe the whole brain and then say how that specific synapse in there should change. So these are very important differences. And I think your point is very, very to the point, but extended a bit to, there are other differences. And then, yeah, the evolution within these different conditions has resulted in these potential advantages. But then in order to make that more concrete, we will have to go into each of them. And then, right, and I guess what...
Yeah. I think that your point on adversarial robustness of your learning rules makes a fair bit of sense. And so I ask this because I'm really curious as to like where the neuromorphic community is kind of going to push towards next and what explosion of learning rules we're going to see. The adversarial robustness is an interesting one, right? I guess that, I don't know, it could be said that if you're maximizing information transfer in something like backprop, then maybe you're learning things that you don't want to learn. You're learning adversaries, you're learning noise that may be irrelevant to your task at hand, whereas these, I guess, methods such as soft head and local learning rules that may not necessarily understand how to overfit to a problem could potentially just be ignoring them or going to your mantra of learning to forget. And I don't know, learning what not to learn seems pretty important as well. Yeah, maybe that's like one of the unexplained reasons as to why these work so well. I'm just shooting random thoughts here.
Yeah. I mean, in the case of some potential way of getting around these adversarial sensitivity is that currently backpropagation is forcing the network, as you said, to learn like the little details that may actually be in reality irrelevant to the concept that the network is supposed to learn. So possibly some like circuit level constraints could force the network to learn concepts as opposed to individual connections, right? And this is actually what's happening in software itself, is that it lets neurons within a layer compete with each other and focus on entire concepts in one way or another, defined in one way or another. And I think that this is what underlies the robustness.
Yeah, very nice. Oh yeah, I'm glad that I multitasked breakfast with this talk. This is awesome. Thanks a lot, man.
Thank you.
Okay, we have another question in the YouTube channel. How do you think? What do you think about the current work that focuses on ANN to SNN conversion with several time steps? Do you think it's just a kind of quantization of the neural network using spike count?
I mean, I think there is a lot of potential in all these methods, and there's amazing work happening. And lately, there has been so many nice pieces of works work on spiking networks, and they're, I think that this approach is can also be very powerful. We need to see, but indeed, it is also likely that maybe the potential advantages of that approach, unless it is combined with some other aspect of spiking neurons. So, for example, if spiking networks operated on use the timing of the spikes on time-based inputs with some additions to it, not just decreasing, counting spikes and so on. So there might be additional benefits that are then also very efficiently implemented by reducing the operations and then making these operations just binary. So it is possible that this direction, with some fine-tuning, might be more than quantization.
Great, thanks. Okay. I'm trying to read among the comments.
I'll come in with another one. I'm not. You didn't focus too much on the hardware, but I'll go ahead and just ask another hardware one. What was there was some memristor stuff in there. What was the biggest pain point of working with memristors in this? So I think from a learning standpoint, they can be quite challenging because of nonlinearity, endurance, a bunch of other stuff. Was there any in particular that shined for you?
Well, I was very lucky to be working with. I mean, I still am very lucky to be working with some of the top groups in these fields of different types of memristors or have very established, lab techniques and instruments and so on. So and also luckily I wasn't the one to be working with the physics.
They protected you.
But I mean, I did use some of them, and some sort of hands-on, but I wasn't the one fabricating the devices. I mean, you already mentioned the important pain points. It is the non-idealities of these devices that you still have to make them work, while each of them is different from the other. It has they have some of these types of devices have limited cycles that you can use, and so these are very well-known problems. And I mean, for me, I wouldn't be able to say something that was unique in my case. It was just so. I think it was in this case we were sort of also again lucky because we observed some properties of these devices that were present in the physics. And then we also had some understanding of some neurobiological mechanisms that match them. And then we saw, wait, I mean, yeah, maybe that's non-ideal and so on, but it can do all that. Let's try and show it. And then we did show it, and it, within its limitations, it worked. So,
yeah. It sounds like a good learning rule, like a good fit for a somewhat stochastic non-ideal device, right? And it could lean back into, I wouldn't call non-idealities adversarial. Maybe it's just like physical adversarial devices. I don't know, noisy devices. Let's just leave it at that. But it could be that these two things are your learning rules are a really good fit for.
Yeah, I mean, it has long been sort of one of the at least before all this overfitting on spiking networks, some of the other promises of the field has been that you will be able to have continuous learning that is able to deal with noisy analog devices. And I mean, I think indeed most likely being able to adapt on the spot should be able to adapt also to these non-ideal hardware.
Yeah.
Okay, from YouTube, I think that's it. I don't see other questions. I have one, but maybe if Gregor has some, please go on.
Not at the moment. Just is there another one on YouTube?
No. I have one, but if you wanted to go on.
No, go for it.
Okay. So my question it's again about spiking and not spiking system, let's say. So I am an hardware guy, so I'm more I always think about I would implement it in hardware, let's say. But as Jason was stating, wasn't I mean, do spiking neural network actually provide would they provide an actual performance improvement if we were able to actually implement a mechanism like your soft herb mechanism to actual artificial neural networks? I mean, why should I go in current system from an ANN to an SNN for my application if I can apply the same methodologies and get better performance in terms of accuracy and so on and so forth? Because as you were saying, rate coding per se, it's not efficient. It's in my view, it's just performing multiplication by several addition steps. So in my opinion, the actual spiking neural networks that might provide an advantage are the ones that are based on latency coding, in which I have a really sparse activity and I can actually do something in the hardware. So why, in your opinion, or is there any way an actual SNN can outperform an ANN if you can apply the same methodologies as you did on those kind of networks?
Right. Yeah. So for one, in that partly spiking network that we introduced, that spiking aspect did bring an advantage compared to the state of the art, right? And it was that it made the networks perform inference faster, but also the training was faster, because you basically, when you provide a sequence, you don't need to see the whole thing before you infer what you saw or listened to, right? You can stop computing in the middle of it if you have a high enough confidence that lets you spike. So that's one thing that I mean, it actually provides an efficiency advantage, and it also provides a speed advantage, and it doesn't need to decrease the accuracy even, right, to achieve that advantage. Now, that was in partly spiking networks, but in the paper we had also like just a proof of concept demonstration. You can also apply it in fully spiking networks, and then yeah, if you combine it with all the recent advances in achieving high accuracy in fully spiking networks, then it would be fully applicable also to fully spiking networks, right? So then you would get the advantages of spiking, potentially even more strongly in a fully spiking network, this advantage of speed. Now, other advantages, I think there are, but again, we need to be careful. I wouldn't be right now. I wouldn't be able to provide a concrete list of things that we should do. But there are things that can be done with spikes, but in a very systematic way. We need to think carefully before going and implementing something in a spiking manner just to make it spiking, and then say, oh, it can be very efficient because it's spiking, and it's also. And then if somebody challenges us and says, well, you can also do it that other way. Then we fall back to say, yeah, but it's also biologically inspired, which also makes it exciting. So this is a very common theme, and it doesn't have to be so if we are careful about which part of the spiking mechanism is going to be useful in our scenario. And there can be useful scenarios. As you said, if you, and as I also said before, if you use time, but this is, you would have to make it more specific. But for example, in the case of the short-term plasticity, where we actually did use spiking networks. In the theoretical proofs of it, we show that actually, if the input is encoded as a Poisson encoded signal, where there's some continuous value that is encoded, but that is also can also be changing continuously, but it's represented in a rate, in a Poisson way, then actually the learning rule that is optimal in that dynamic setting I was showing, let me maybe go back there, it is actually an STDP, a short-term STDP rule. So it needs the spike timing in order to actually optimally model that sensory input that is coming from that is encoded in a Poisson. So, and there are many sensors that actually provide outputs in a Poisson manner. For example, there are like light sensors that are responding to individual photons and so on, and these are very noisy, but they're very accurately modeled as Poisson. Well, there you would need a spike timing dependent learning rule to optimally model it. And that's just one example, right? Where the sort of timing of the input needs to be represented in a timing in the network. There might be also other scenarios where that is. There certainly are other scenarios where if you use suitably time-coded neurons, you could optimally model the time dynamics of the input. Yeah. And that would make spikes advantageous. That's the point. Yeah.
Okay, thanks. That's it for me. And I don't see any other questions in the chat at the moment. Yeah.
Well, all right then.
Okay, if Gregor does not have any questions, I think we can close it here. Thank you very much, Timoleon, for taking the time to do this talk. It was really, really interesting. I totally agree with Jason on this. And thanks again, and have a good evening in this part of the world, let's say. Okay.
Great, thanks. It was a pleasure for me too. Have a good one. Bye.
Thank you very much. Bye-bye.
Bye bye.